This is chapter number 6, Electromagnetic Induction. We are taking question and answer on electromagnetic induction. The first one is predict the direction of induced current in the situation described by the following figures. So we have to predict the direction of induced current. So these are the situation. We'll see one by one. First of all, we have to understand the Lenz's law. The direction of the induced current in a closed loop is given by the Lenz's law. Now the given pair of figures here, we have pair of figures here, shows the direction of induced current when the north pole of a bar magnet is moved towards or away from a closed loop respectively. What is happening? That when we are bringing the north pole, so this N will show the direction of the current. When we are, you can say, taking it away from this figure or this loop coil, then it will make sounds. So this will be the direction of current. So we'll use the Lenz's law, and the direction of the induced current in this situation we can predict it here. What will be the direction? See, we are bringing it. So when we are bringing it, the direction of induced current will be along Q, R, P and Q, like this. Okay. So it is going to make a north, like this, right? So this is how it is going to be. As I suggested here, we are bringing the pole or the magnet. In the similar fashion, when we are taking it away from this point or bringing it near this point, so what will be the direction of the current? It will be P, R, Q and P, like this. Again, this one, C. So the direction of induced current will be what? It will be Y, Z, then X, Y, means in this direction. Okay, because this is a common axis and you are tapping key to close it. Then we have this one. The direction of induced current will be along what? It will be Z, Y, X, Z. It will be in this direction, Z, Y, X, Z. Because now, in this case, the current is going like this. Here the current is moving like this. So this will be just the opposite of it. Now this one, E. What will be the direction of induced current? It will be X, R, Y and X, like this. This will be the direction of current. This is the tapping key. When we just tap it, so there will be a flow of current, and because of this, a magnetic field will be induced, and because of this, current will flow here. And here, in this case, there will be no current which will be induced, since the field lines, these are lying in the plane of the closed loop. This is a closed loop and these are the field lines. So this will not have any induced current. A 1 meter long metallic rod is rotated with angular frequency this much, about an axis normal to the rod passing through its one end. The other end of rod is in contact with a circular metallic ring. A constant and uniform magnetic field of 0.5 T parallel to the axis exists everywhere. We have to calculate the EMF which is developed. This one we have to find. EMF developed between the center and the ring. So what all is given, let us write. This is 1 meter. So L, that is the length of the rod, is 1 meter. The angular frequency is 400 radian per second. So let us write omega as 400 radian per second. Then we have the magnetic field which is given here, B, which is 0.5 Tesla. Now according to the question, one end of the rod has zero linear velocity. while the other end will have a linear velocity, which is what? Length into omega. See, there is a long metallic rod rotated with angular frequency, and the axis is normal to the rod passing through its end, right? This is the one point will have zero linear velocity, but the other end will have proper L omega. So what will be the average velocity? Because if this is a rod, this is fixed and this is moving. So what will be the average linear velocity? It will be 0 at one point, L omega, that is R omega. R, for R we have taken the length, L omega. So L omega plus 0 by 2. So L omega by 2 will be the average linear velocity. Now what will be the EMF developed? Because we are talking about the between the center and the ring, because here it is forming because the other end of the rod is in contact with a circular metallic ring. So we have the EMF which is developed between the center and the ring. The center and the ring. So this will be B into L into V, and BL is okay. We can use like this, L omega by 2. We have to find the average linear velocity. So it will be BL square omega by 2. All these values are known to us. See, just put it. We get EMF as 100 volt. A long solenoid with 15 turns per centimeter has a small loop of area this much, placed inside a solenoid normal to its axis. If the current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 second, what is the induced EMF in the loop while the current is changing? So what all are given? Let us write this. Number of turns in the solenoid is 15 turns per centimeter. We converted it into meter, so it will be 1500 turns per meter. So we have to find out the number of turns per unit length, because this is what we use in our formula. This will be 1500. This is turns per unit length, 1500. So we will take this value. Now this solenoid has small loop which has area which is given here. It is 2 centimeter square, so we will convert it into meter square. Now current carried by the solenoid, it changes from 2 to 4, so 2 ampere to 4 ampere. So what is the change in the current in the solenoid? We have to find out the difference, that is DI. Change in or delta I or DI. So this will be 4 minus 2, which is 2 ampere. Now what is the change in time? It happens in 0.1 second. Now let us come to the Faraday's law. The induced EMF in the solenoid is given by the Faraday's law, which is E equal to d phi by dt. What is this phi here? This is the induced flux through the small loop which is being said in the question. So what is phi? Phi is actually B into A, and B is the magnetic field, and we know in the pretext of the question that B for this scenario will be mu 0 Ni. Mu 0 is the permeability of free space, which we take this value. Now what equation will become? The equation will become E equal to, for phi we will write B into A, and for B we will write mu 0 Ni. So put all this value. We take A mu 0 N outside, and this di by dt will remain inside. Now di by dt, di is 2, dt is 0.1 second as we just said. 4 minus 2 is 2, and this dt is 0.1. Other values we are aware of. Put this and we get the induced voltage to be 7.154 into 10 to the power minus 6 volt. A rectangular wire loop. This is a rectangular wire loop. 8 is this side, 2 is this side. So a wire loop of side 8 cm and 2 cm with a small cut is moving out of there is a cut, is moving out of a region of uniform magnetic field of magnitude 0.3, which is directed normal to the loop. So you can say like it is coming outside or it is going inside. What is the EMF developed across the cut? So if there is some cut, if the velocity of the loop is this much in a direction which is normal to the longer side, that is this much, this one 8 cm, and shorter side, that is 2 cm. For how long does the induced voltage last in these two cases? So the length is 8 cm, convert it into meter. Width is 2 cm, let us convert it into meter. Now the area of the rectangular loop will be length into breadth. It will be simply 0.08 into 0.02, that is this value. Now the magnetic field strength is also given 0.3 Tesla of the loop, and V is also given the velocity with which it is moved. So let us convert it into meter. So this will be 0.01 meter per second. So we'll take the first part, that is the A, and the second part we'll take for the, because the dimension are different. So the EMF which is developed in the loop here, the length BLE equal to BLV. In this, B will take 0.3, but L will take it as 0.08, because now the first part is about this length. So B into L into V, V is already we have taken, so this will be the value. This is the induced, this is EMF which is developed. Now the time taken to travel along the width, again we'll take this, because the width is 0.02, which was initially 2, so we converted into the proper unit, and this becomes 0.08. Now the time taken to travel along the width will be what? So we have to take the distance as 0.02, and velocity, of course we have a velocity, so put it here, it will be 2 seconds. So the induced voltage is this much for this much of time. So 2.4 into 10 to the power minus 4 volt, which lasts for 2 seconds. The second one is same thing we'll do, now we'll do for this side. Okay. So when induced EMF, we are talking about EMF being developed, so we take BLV, and in this case the length will be this side, which is 0.02 will take. So we put these values, this is the EMF being developed, but now this side has to pass. So the time taken to travel along the length, which is 0.08, will take distance as 0.08, velocity will remain like this, same velocity will be L by V, which is 0.08 by 0.01. So the induced voltage of this volt will last for this seconds. A circular coil of radius 8 cm and 20 turns is rotated about its vertical diameter. So there is a circular coil. This is the vertical diameter. The circular coil of these values is rotated. So it is rotated like this along the vertical diameter with an angular speed which is given here, omega, 50 radian per second in a uniform horizontal magnetic field. Now the magnetic field is like this. The value is this much. Obtain the maximum and average EMF induced in the coil. If the coil forms a closed loop of resistance which is given as this much, calculate the maximum value of current in the coil. Calculate the average power loss due to joule heating. Where does this power come from? So what all are given to us? We'll write the value. The maximum induced is this much, average is this much, maximum current in the coil is this much. These are the answers. But how do we get this answer? What we have to do here is, the average power loss is also there. So we'll put one value and then start computing it. How do we arrive at these values? So the radius is given as 8 cm. We are putting these values, all these values we are writing just. So radius is 8 cm, we will convert into meter. Because it is a circular coil, so the area will be pi r square. This radius is now 0.08 meter. So pi r square, this will be the area. Now number of the turns are 20, which is already given in the question. Angular velocity omega is there. Magnetic field strength is this, radius is this. Now the maximum induced EMF for circular coil will be N omega AB. N you know, omega you know, then area pi r square you know, and B is also given. So this will be 0.603 volt. So the maximum induced EMF is 0.603 volt. Now over a full cycle, the average EMF induced in the coil will be 0 when it comes again, right? What will be the maximum current? This is given by EMF by resistance. So 0.603 divided by the resistance, which is 10. This much. So we get this as the current, maximum current. Now what will be the average power loss due to joule heating? Power will be VI by 2. So this will be that is EI by 2. E is induced EMF. E into I by 2. This is the value of power loss. So the current which is induced in the coil, it produces a torque opposing or in the other direction to the rotation of the coil. So the rotation is an external agent. So it must apply a torque to counter this torque in order to keep the coil rotating uniformly like this. So the dissipated power comes from the external rotor or rotator. A horizontal straight wire 10 meter long extending from east to west is falling with a speed of this much at right angles to the horizontal component of the earth magnetic field, which is given by this value. So what is the instantaneous value of the EMF induced in the wire, and what is the direction of the EMF, and which end of the wire is at the higher electrical potential? So what all value are given? This is length, and this is the velocity, and this is the magnetic field. Let us write them. Now EMF induced will be, we know about a wire, E will be BLV, B is known to us, L is known to us, V is known to us, this will be this value. Now we can use the Fleming right hand rule. Now by Fleming right hand rule, we can easily infer that the direction of the induced EMF will be from west to east, and the eastern end of the wire will be at higher potential. Current in a circuit falls from this value to this value, 5 to 0.0 in 0.1 second. If an average EMF of 200 volt induced, given an estimate of the self-inductance of the circuit. So in this case, the initial current, this is I1 is 5 ampere, I2 is 0 ampere. So what is the change in the current? Di will be I1 minus I2, that is 5 minus 0. The time, this is the time taken to change, that is 0.1. So the average EMF is also given. Now the self-inductance L of the coil, we know that we have a relation of average EMF, and this is equal to E equal to L di by dt. Now in order to find L, we will divide di by dt with E. E di by dt, E is known 200, di is 5 from here, and this dt is 0.1. So we get 4. This is the self-induction of the coil, which is 4H. A pair of adjacent coils has a mutual inductance of 1.5 Henry. If the current, that is I, in one coil changes from 0 to 20 ampere in 0.5 second, what is the change of flux linkage with the other coil? So what all are given to us? Mu, mutual inductance is given. The initial current is I1, the final current is I2. So we will take the change in current 20 minus 0, which is 20 ampere. So the time taken to change is also given 0.5 seconds, so it will be our dt or t. So in this EMF we know that E equal to d phi by dt. D phi is what? D phi is the change in the flux linkage with the coil. So we have a relation, EMF is related to the mutual inductance by E equal to mu di by dt, right? We'll put E equal to d phi by dt here in this case. So d phi by dt equal to mu di by dt. So d phi will be equal to mu di is 20. Just multiply this mu 1.5 by 20, you get 30 Weber. A jet plane is traveling towards west at a speed of 1800 km an hour. What is the voltage difference developed between the ends of the wing having a span of 25 meters? So if the Earth's magnetic field at the location has magnitude this much, and the dip angle is 30 degrees. So the speed of jet plane is this much. We can convert it into, by multiplying by 5 by 18, so we can convert it into meter per second. Now wingspan is 25 meter. The Earth's magnetic field strength is also given, and angle of dip is 30 degrees. So we need to understand that we have to use the vertical component of the Earth magnetic field, which is BV equal to B sine of this angle. So B is known to us, and sine angle will use 30 degrees. So this will be the BV, B vertical component. Now the voltage difference between the ends of the wing, see if this is an aircraft like this, This is the aircraft, these are the wings. These are the wings. We have to find out the voltage difference between these two ends. So it will be E into B into L into V. Here we will take B as the vertical component. So L into V, this we just found out, L and V are known to us. Just put it here. The voltage difference developed between the end of the wings will be 3.125 volt. So this is the first part of these question answers. We'll be taking one more. Till then, thank you so much. Take care of yourself.